Imagine standing beside a dirt road in America in the 1910s. A motor car passes in front of you, and the sound that strikes your ear is not the engine. It is a piercing, high-pitched howl from the rear axle, loud enough to swallow nearly every other noise the vehicle makes. The driver can do nothing about it. The manufacturer can do nothing about it. That howl is the voice of straight bevel gears, the only practical technology the young automobile industry has for turning engine power toward the rear wheels. And for a time, the entire industry accepts it as an unavoidable fact of mechanical life. Now jump ahead to the 1930s. The roads are still there. The cars are faster, heavier, more powerful. But now they glide past in something close to silence. The howl has disappeared. The machine that helped make that awful sound vanish was the number 16 Spiral Bevel Gear Generator from Gleason Works. It did something that had previously lived mostly in theory or in the hands of a few master craftsmen. It taught metal how to turn power through a right angle smoothly, accurately, and in mass production. It did it so well that both the American automobile industry and the United States military would line up to buy what Rochester could build. As always, don't forget to like this video, share it, and subscribe to the channel so you'll be notified whenever we release another story from the hidden world of industry. For now, we are going to look at a machine without which the modern automobile would look different, drive different, and perhaps even the logistics of 2 world wars would have followed a different script. It was a machine at the foundation of industry, invisible to the public, but present in every turn of countless wheels for more than a century. To understand why this machine had to be invented, we have to begin with a geometry problem that every rear-wheel drive automobile must solve. The engine sits at the front. The drive shaft runs lengthwise beneath the body, but the wheels rotate around an axle running across the car. Somewhere inside the rear axle, the engine's power has to turn a corner. It has to make a 90-degree turn, and the only components capable of making that turn are a pair of bevel gears, 2 cone-shaped gears meshing at right angles, quietly redirecting the entire force of the machine. The problem was that the available technology, straight bevel gearing, meshed in a brutally direct way. Each tooth struck the next like a hammer blow, one after another, thousands of times per minute. That continuous chain of impacts produced noise, vibration, rapid wear, and most importantly, a hard limit on how fast and refined the automobile could become. If cars were to become faster, quieter, and more durable, the industry had to overcome the gears inside the rear axle. The irony was that the theoretical solution already existed. If the teeth of a bevel gear could be cut in a spiral instead of a straight line, several teeth would mesh at the same time. The load would be shared. Power would flow more like water than like a series of blows. Engineers understood this. Drawings could prove it, but between knowing something and producing it lay an enormous gulf. No one could cut spiral teeth on a conical surface with the speed, accuracy, and repeatability required for mass production. A master craftsman, given enough time and patience, might make a pair of spiral bevel gears by hand. But Ford was building thousands of cars a day, and each one needed gears in the rear axle. The missing piece of the era was not the idea. It was the machine that could turn the idea into production. This is where Gleason Works enters the story. The company had been founded in Rochester, New York, by William Gleason, and had made its name with the family's bevel gear planer. His daughter, Kate Gleason, the first woman to become a member of the American Society of Mechanical Engineers, played a crucial role in bringing the family's machines to the rapidly expanding automobile industry. By the time the spiral bevel problem became urgent, Gleason had become something like the cathedral of bevel gearing, the place the industry looked to when the hardest problems in this field needed solving. But even that cathedral did not yet have the answer to spiral teeth. Gleason faced the familiar choice of every leading company: break through its own limits or wait for someone else to do it first. The common instinct of the time, when faced with a complicated tooth shape, was to create an equally complicated cutting tool. If you wanted to cut a curved groove, you made a cutter that already carried the curved shape, then pressed that shape into the workpiece. It sounded reasonable until you thought about replication. A cutter with a complex form was difficult to manufacture, difficult to resharpen, and every time it wore down, the shape it left behind changed slightly. The result was that each gear came out a little different from the one before it. And in the world of mass production, a little different meant failure. The path of the complex cutter died at the gate of repeatability. The engineers at Gleason took the opposite path. It was generated by the coordinated motion of the workpiece and the cutter head, rolling together according to a precisely calculated law, as though the workpiece were meshing with an imaginary crown gear. In other words, the machine did not simply carve a tooth into metal. It reenacted the motion of gears meshing with one another and allowed geometry to do the rest. The elegant spiral curve on the conical surface was not drawn by hand. It was the unavoidable result of controlled rolling motion, just as a wheel leaves a track in sand because it has rolled across it. The true beauty of the solution was that it moved the location of accuracy. In the old way of thinking, accuracy lived in the cutting tool, a thing that wore down every day and changed every time it was sharpened. In the generating method, accuracy lived in the machine's kinematic chain, the gears, shafts, cams, and synchronizing mechanisms that controlled the movement between the cutter and the workpiece. That chain could be built with extraordinary precision once, then used to repeat the same geometry thousands or millions of times. Cutters could be replaced, blades could be sharpened, but the geometry of the machine remained fixed. As a bonus, the rotating cutter head solved the problem of speed. Older gear planers cut with a reciprocating stroke, meaning that half the time was spent on the return stroke, cutting nothing at all. A rotating cutter head cut continuously. One blade left the workpiece just as the next one entered. On paper, the solution was perfect, more accurate, faster, and far easier to reproduce. But the distance between a perfect principle on a drawing and a working machine on a factory floor is where great engineering stories truly begin. Because that same rotating cutter head, the most elegant feature of the entire design, would become the source of the first enemy Gleason had to defeat: vibration. The generating principle looked beautiful on paper, but on the shop floor it was merciless. It forgave nothing in the machine built to carry it. Gleason's engineers entered the development phase fighting on 3 fronts at once, and each front left visible traces on the final form of the number 16. The first front was rigidity. The continuously rotating cutter head, the design's most elegant solution, was also the source of its first danger. Many cutting blades mounted around a spinning disc meant that cutting force was never perfectly smooth. Each blade entered the metal with a blow. As one blade left, the next struck, hundreds of times a minute. Early prototypes vibrated under that repeated impact, and vibration in a bevel gear machine was not a harmless flaw. It printed microscopic waves onto the tooth surface. when a pair of gears carrying those waves rolled together beneath a car at thousands of revolutions per minute, those tiny errors would sing out as exactly the sound this machine had been created to destroy: the rear axle howl. A machine designed to cure noise could not be allowed to create noise of its own. The lesson was cast directly into the body of the machine, almost literally. Massive iron castings, box-like enclosed structures, weight concentrated around the cutting zone to absorb each pulse before it could spread. Anyone standing today in front of a surviving number 16, seeing its heavy, stubborn, almost crude silhouette, should understand that this was not a matter of aesthetics. It was the scar tissue of vibrating prototypes, fossilized in cast iron. The second front lay deep inside the machine, the drivetrain. The entire philosophy of generating depended on one condition: the rolling motion between the workpiece and the cutter had to be synchronized absolutely, as though two real gears were meshing. That condition turned every intermediate gear, every shaft, every coupling inside the machine into a link in the final accuracy of the product. A tiny amount of backlash anywhere in that chain did not disappear. It traveled straight into the tooth geometry and was faithfully reproduced in every gear the machine produced. Here the engineers in Rochester faced an almost cruel paradox. To build a machine capable of cutting precise gears, they first needed precise gears to put inside the machine. No outside supplier could meet the standard they required, because that standard barely existed yet. Gleason had to raise the entire level of its own internal manufacturing. It used the best machines it had to make parts for better machines, then used those better machines to raise the standard again. That self-improving loop continued through generations of prototypes. It was slow, expensive, and demanding. But it was also how a factory in Rochester pulled itself upward until it held one of the highest standards of precision in the industry. The third front was not metal, but people. Every gear ratio, every cone angle, every spiral direction required a different set of machine settings. If only master craftsmen could set the machine correctly, then mass production would still be nothing more than handicraft dressed in machinery. Gleason understood that it could not sell a machine that required 10 years of apprenticeship to operate. The answer was to package knowledge, standardized calculation tables, step-by-step setup procedures, documentation that transformed the experience of the Rochester engineering office into something an ordinary operator could look up and follow. The machine became more expensive and more complex inside, so that the person standing in front of it could work more simply. It was a deliberate trade-off, and as the next part of the story shows, that trade-off was what opened the door to Detroit. The moment the machine truly came alive was not simply when the first pair of spiral bevel gears ran more quietly than straight tooth gears, although that alone was a victory. The decisive moment came a little later, when people placed the 100th pair beside the first and realized they were the same. Quiet operation was what spiral gearing had promised in theory. Identical results across hundreds of repetitions were what only this machine could deliver. To understand the scale of that achievement, place two worlds side by side. Before the number 16, a good bevel gear set was the work of a highly skilled mechanic. Each pair had to be hand-lapped and matched. The pinion and gear were bound together like an arranged marriage. If one failed, the other was often useless. After the number 16, gears became products of machine geometry, and the consequence, simple as it sounds, shook the foundations of manufacturing. Any pinion could mesh with any gear of the same specification. Interchangeability, the condition that Detroit's assembly lines demanded from every component, from bolts to crankshafts, had finally reached one of the most difficult parts of the automobile. For the machine operator, the trade changed at its roots. What had once been a metal-cutting craft requiring years of training became a process of setting the machine from tables, loading the workpiece, and starting the cycle. One person could tend several machines. Accuracy no longer depended on whether a craftsman's hand was steady that day. But spiral teeth gave the automobile industry a second gift, one that is mentioned less often. Because multiple teeth shared the load at the same time, a spiral bevel gear set of the same size could transmit much more torque than an equivalent straight bevel set. Designers suddenly had room to move. Engines could become more powerful without making the rear axle larger, or the axle could shrink while keeping the same pulling power. Floors could be lowered. Centers of gravity could drop. The shape of the automobile itself began to change. A machine standing in a Rochester factory, one that never traveled a single mile under its own power, quietly redrew the lines of every car on the road, and the generating principle proved fertile. Gleason went on to develop the hypoid branch of the technology, offset bevel gearing that allowed the drive shaft to sit lower than the center of the axle, lowering vehicle floors even further. A correct principle does not merely solve one problem, it gives birth to a whole new generation of technologies. As the major automobile companies shifted rear axles first to spiral bevel gears and then to hypoid gears, buying Gleason machines was no longer simply a technical choice. It became a condition of participation. You could not sell a howling car in a market filled with quiet ones, and you could not build quiet cars without the machines from Rochester. Each axle production line needed not one machine but a whole sequence of Gleason equipment. Roughing machines, generating machines, grinding machines, inspection machines. Every time a new axle line opened anywhere in the world, orders flowed toward the same address. Rochester became the golden bottleneck of the global automobile industry. Gleason machines crossed the Atlantic and stood inside the factories of European companies competing against American cars. It was a rare and enviable position for an equipment builder. The customer's rivals were also customers. Modern war ran on spiral bevel gears in the most literal sense. Tanks needed them in final drives. Military trucks needed them in axles. Warships needed them in power transmission assemblies. Aircraft needed them wherever power had to change direction inside the tightest possible spaces. All of those needs, no matter which uniform or insignia they served, led back to the same source of machinery. During the Second World War, America's capacity to cut bevel gears was closely tied to the production capacity of Gleason Works. The plant ran at full force for national defense, and thousands of Gleason machines, spread through workshops across the country, became a true infrastructure of war. They were invisible on campaign maps, but present in every vehicle that rolled toward the front. And here, a geometrical decision made years earlier in a Rochester design office revealed consequences that even its creators may not have fully foreseen. Interchangeability, the direct result of the generating principle, turned battlefield repair from a craft into a logistical operation. A tank with a damaged axle no longer had to wait for a mechanic to hand-match a pair of gears. A repair unit could pull the correct part from stock and install it, because every gear of the same specification would mesh as though it had been born for the other. In a geometric sense, it had. An army that can return damaged vehicles to service faster gains an advantage that cannot be measured in the caliber of its guns. The spiral curve cut into a conical gear, first developed to kill an unpleasant automotive howl, ended up helping shape the way mechanized war was supplied and sustained. But every peak has another side, and the near monopoly Gleason had built would soon face waves of change that no block of cast iron, however heavy, could hold back. The position Gleason held after the 2 world wars was rare in the history of machine tools. In most segments, even a leading manufacturer has to live with several serious competitors, negotiate standards, and share technical authority. In the world of spiral bevel gears, Gleason was almost the world itself. The company defined inspection standards. It established terminology engineers everywhere had to learn. It wrote the procedures factories followed if they wanted their machines to run properly. An axle plant in Michigan, a gearbox factory in Europe, a defense facility somewhere else entirely. All of them spoke the same technical language, and that language had been written in Rochester. This dominance lasted for decades, long enough that many inside the industry almost forgot it could end. But industrial history grants immunity to no empire. For Gleason, the challenge did not arrive as one blow. It came in 3 waves, each attacking a different pillar of the company's power. The first wave came from across the Atlantic. European manufacturers, especially Klingelberg and Oerlikon, did not merely try to copy Gleason's path. They developed their own, continuously generated spiral bevel tooth systems based on a different geometrical philosophy from the Rochester method. The technical details of these competing schools could fill textbooks, but the strategic meaning can be summarized simply. For the first time, customers had a real choice. A European factory that wanted to cut spiral bevel gears no longer had to order from America. It could buy machines from a supplier on the same continent with its own philosophy, its own service network, and its own engineering pride. The world market was divided again. The 2-school rivalry that emerged from that competition still exists today, with engineers debating the advantages of each system much as connoisseurs might debate 2 wine regions. Gleason remained large, it remained powerful, but from the position of being the only one, it became one of 2. For a company that had once defined an entire industry, that erosion mattered. The second wave was more dangerous because it did not attack market share. It attacked the reason the machine existed. Remember what had made the number 16 valuable. All of its accuracy lived in a mechanical kinematic chain, in hundreds of gears, cams, shafts, and carefully built linkages that synchronized the motion between workpiece and cutter. That mechanical maze was the treasure. It was what competitors could not copy quickly. It was the accumulated result of self-improvement across generations of machines. Then CNC arrived, and it did exactly what the kinematic chain had done, but with servomotors and software. The coordinated rolling motion between cutter and workpiece, which had once required an entire orchestra of precision mechanical elements, could now be described in lines of code and executed by numerically controlled motors. Fewer mechanical parts meant fewer sources of error and fewer components to wear. Software setup meant switching from one gear ratio to another in minutes, rather than spending hours changing gears and settings. Greater flexibility meant that one machine could serve a range of products a purely mechanical generation could never have imagined. For Gleason, this was an almost cruel reversal. Nearly a century of accumulated knowledge in precision mechanical linkages, the company's most valuable asset, was at risk of becoming a burden. To cling to it was to cling to the past. To release it was to release part of the company's identity. The third wave did not target Gleason alone. It swept across the entire American machine tool industry in the 1980s. Japanese manufacturers entered the market with standardized CNC machines, fast delivery, competitive pricing, and quality that became increasingly difficult to dismiss. Economic downturns choked off orders in a capital equipment industry already defined by brutal cycles. Financial pressure forced companies to prove their value quarter by quarter rather than decade by decade. The list of famous names damaged or destroyed by that storm is painfully long. Companies that had once equipped American industry collapsed, were acquired, broken apart, or shrank into shadows of themselves. Anyone watching the industry at the time had reason to believe Gleason, whose core product was tied so deeply to mechanical precision, might be the next name on the list. But Gleason did something fundamentally different from many of its contemporaries. It did not cling to old iron. The company's leadership recognized a truth that many rivals discovered too late. Gleason's real asset had never been cast iron or steel. It was geometry. Almost a century spent solving the problem of tooth forms on conical surfaces had created a deep reservoir of knowledge about gear meshing, spiral geometry, contact patterns, and the prediction and correction of how two gears would meet under load. That knowledge did not depend on whether the motion was created by mechanical gears or electronic servos. Gleason transformed that inheritance into software, the algorithms that calculated tooth geometry, the tools that simulated contact patterns, the entire brain once embodied in the mechanical chain of the number 16 was rewritten as code and installed inside new CNC machines. At the same time, the company changed structurally, combining with another major player in gear technology to form Gleason Corporation, a global organization large enough to survive in a transformed market. The fate of the number 16, then, was not really death. It was reincarnation. The mechanical machine was replaced, as all technologies eventually are. But the intelligence inside it, the geometry hardened through millions of gears, moved into a new body and continued to live. Return one last time to that dirt road in 1910 and to the piercing howl from the rear axle of an early automobile. That sound has vanished so completely that almost no one remembers it was ever there. There is no monument to a dead noise, no anniversary for a defect that has been cured. But that absolute forgetting may be the highest measure of success for a foundational technology. When a solution works so well that the problem it solved disappears from collective memory, when an entire generation grows up never knowing that cars once screamed from their rear axles under power, the technology has reached its final destination. It has become obvious. The legacy of the Rochester machine exists on three levels. The first is physical, and it is tangible enough to touch. Some number 16 machines and their mechanical descendants are still running today in small gear shops, vintage vehicle restoration workshops, and certain defense facilities. The reason is not nostalgia, it is pure economic logic. For small production runs, a 70-year-old cast-iron machine that has long since paid for itself and that still holds accuracy through its mass and construction can be far more sensible than a modern CNC investment. The heavy, stubborn body that began as the scar tissue of vibrating prototypes became its ticket to a very long life. Castings poured to absorb vibration in the 1920s are still absorbing vibration in the 21st century. The second level is knowledge, less visible than iron, but perhaps more durable. The terminology Gleason built around these machines, the calculation methods, the standards for inspecting contact patterns, All of it remains part of the common language of bevel gearing around the world. An engineer in Germany, Japan, or China today, sitting down to design a spiral bevel gear set, can still speak of the Gleason system as a school of thought, comparing it with the European systems as parallel frames of reference. Very few companies in industrial history leave a mark at this level. Not merely a remembered product, but an inherited way of thinking. People may stop buying your old machines, but if they still think in your concepts, your legacy is still operating. The third level is presence, and it is so widespread that it becomes almost invisible. Every pickup truck towing a load down a highway, every rear-drive SUV, every long-haul truck, every helicopter suspended in the air, every place where power must turn a corner inside a cramped mechanical space, there we find descendants of what that Rochester machine helped make possible. Even the age of electric vehicles, in which many drivetrain architectures no longer require the same bevel gear arrangements, only clarifies the scale of the story rather than diminishing it. When a technology begins to yield only after dominating an entire century of the automobile, from the earliest mass-produced cars to the last generations of internal combustion vehicles, that retreat is not failure. It is a completed term of service, longer than the reign of most inventions in mechanical history. William Gleason cut his first bevel gears in a small shop in Rochester, in an age when few could imagine metal transmitting power through a right angle smoothly and by the millions. The machine carrying his family's philosophy did exactly that. It taught metal how to turn a corner, and then the mechanical world turned with it, toward quieter cars, faster logistics, better supplied battlefields, and factories that believed precision could be reproduced almost without limit. The howl died long ago. What replaced it is still turning quietly beneath hundreds of millions of machines across the planet. If you want to hear more stories about the machines that quietly built the industrial world, don't forget to like this video, share it, and subscribe to the channel. Thank you for watching, and I'll see you in the next video.